Hi, this is Sonia Doucette. In this video, I'll show you how to find the equilibrium constant Kc from concentration data, and also, once you have Kc, how to find Kc prime from that. So the first thing you want to do here is write the equilibrium equation. So the problem is, at 1000 degrees Celsius, the equilibrium concentrations for the reaction carbon monoxide gas plus 3 hydrogen gas molecules gives you methane gas plus water as a gas. And you know that the concentration of all of those products and reactants are carbon monoxide with a concentration of 0.0613, hydrogen has a concentration of 0.1839 molar, methane is 0.0387, and water is 0.0387 molar as well. So the question is asking, what is Kc for this reaction at 1000 degrees Celsius? So let's find Kc first, and then we'll find Kc prime. The first thing you want to do is write the equilibrium equation. Now, when you're writing equilibrium equations in general, it's important to remember what to include and what to omit. So the things that you want to include are gases and molecules and ions in solution. So anything with a subscript of G, which indicates a gas, or anything with a subscript of AQ, designating aqueous, which would mean something in solution, such as a molecule or an ion. You also want to remember what to omit. So you want to omit two things. You want to omit pure solids, so anything with a subscript of S, and also pure liquids, so anything with a subscript of L. In this case, all the reactants and products are gases, so everything will be included in the equilibrium equation, and we're not going to omit anything. So the first thing you want to do when you're writing an equilibrium equation is you want to include on the left side the equilibrium constant Kc, and that is going to be equal to the equilibrium expression. The equilibrium expression is the name given to the right-hand side of the equation, which shows the concentration of products divided by the concentration of reactants. So in this case, the concentration of products will be methane gas multiplied by the concentration of water. So those are the two products in this case. And then you want to divide those products by reactants. So in this case, you have carbon monoxide gas being multiplied by hydrogen gas, the two reactants. And you also have to raise hydrogen gas concentration to the third power in this case. So any stoichiometric coefficients are going to become superscripts in the equilibrium equation. So if you look back at the balanced equation, you can see that hydrogen gas has a subscript of 3. I'm sorry, it has a coefficient of 3, therefore it will have a superscript of 3 in the equilibrium expression. So there you have it. There's your equilibrium expression, and now all you have to do to find Kc is substitute in your values. So the concentration of methane that you're given is 0.0387 molar. Now all the concentrations when you're finding Kc must be in moles per liter or molar. If it's in any other unit, then you have to do some converting, but in this case all of the concentrations that were given are in molarity, so we don't have to do any converting. The concentration of water that you're given is also 0.0387 molar, and then you're going to divide the two concentrations of the products by the reactants. So the concentration of carbon monoxide is 0.0613 molar multiplied by the concentration of hydrogen gas, which is 1839, and that will be raised to the third power. So if you do the math there, your Kc value will turn out to be 3.93, and that's 3 significant figures according to the initial concentrations that we were given. So the next thing that you can do now that you have Kc is you can find Kc prime. So Kc prime is defined simply as 1 over Kc. So all you have to do is take that Kc value that you found, 3.93, and divide it into 1. And what you'll get when you do that is 0.25. 5, 5. So why would you want to find a Kc value? So it basically tells you what the equilibrium constant would be if you wrote the reaction backwards. So in this case, if we made the products the reactants and the reactants the products, we'd end up with this reaction. We'd have methane gas, sorry, that should be a 4, as a reactant plus water as the other reactant, going to carbon monoxide gas as a product, and hydrogen gas also as a product. So the value 0.255 would actually be the Kc value for this equation, but it's the Kc prime value for that initial equation for which we initially solved for the Kc. So that's it.